Pick a direction. Any direction. Point at the wall in front of you. Now imagine you kept going. Not through the wall, through the wall, through the building, through the city, through the atmosphere and the vacuum beyond it. Imagine you had a spacecraft waiting outside right now, fueled and pointed in whatever direction you chose, and you got in and you started moving. You started moving at the fastest speed any human being has ever travelled, and you kept going for the rest of your life, every day of it, moving in that direction, never stopping, never slowing. How far would you get before you died? Whatever number just came to mind, it is almost certainly wrong. The correct answer is specific and measurable and stranger than almost anything you could have guessed. Tonight we are going to find it. Not the inspirational version, not the science fiction version, the actual version where the numbers are honest and the physics does not negotiate, and the distance between here and the nearest star is exactly as large as it is whether we find it comfortable or not. Where are you right now? What time is it? Hold those answers. Because what comes next is going to change the relationship between your coordinates and the night sky above you. This is not an abstract question. It has a specific numerical answer, or rather a range of answers depending on the technology. The lower bound is set by what we have built. The upper bound is set by the laws of physics. Between those two bounds is the entire history of human technological development still waiting to happen. Tonight, we trace the range from end to end, not to depress you with the lower bound, to show you what the upper bound actually is and what it would take to close the gap. The gap is large. The physics is not the obstacle. What the answer depends on, completely, is the engine. The fastest any human being has ever moved relative to Earth is approximately 39,897 kilometers per hour. The crew of Apollo 10, returning from lunar orbit in May 1969, hit that speed as their capsule fell toward the atmosphere. It remains the human speed record. Nothing built with a crew aboard has gone faster in the 55 years since. 39,897 kilometers per hour sounds fast. It is fast. It is about 11 kilometers per second. It is fast enough to circle the Earth in a little over an hour. Fast enough to reach the Moon in about 9.5 hours. Fast enough to reach Mars at its closest approach in a few months. Now, a lifetime. If you're 30 years old and you live to 80, you have 50 years left. 50 years at 39,897 kilometers per hour, moving in a straight line, never stopping, is a distance of approximately 17.5 billion kilometers. That sounds enormous. It is not enormous. The distance from Earth to the Sun is 150 million kilometers. You would travel roughly 117 times the Earth-Sun distance. Pluto, at its farthest from the Sun, is about 49 times the Earth-Sun distance. You would pass Pluto's orbit in a few years and keep going, reaching roughly the inner edge of the Oort cloud, the vast shell of icy bodies at the outermost boundary of the Sun's gravitational influence. You would not leave the solar system, not in any meaningful sense. The heliopause, the boundary where the Sun's solar wind gives way to interstellar space, is about 120 times the Earth-Sun distance. You would not reach it. The Voyager probes, launched in 1977, reached the heliopause in 2012 after 35 years of travel. At the Apollo 10 speed, starting now, you would die inside the bubble the Sun blows around itself in interstellar space, never having left the neighbourhood. This is the starting point. This is the human speed record and what a lifetime of travel at that speed actually buys you. The nearest star is 4.24 light-years away. 1 light-year is about 9.46 trillion kilometers. Alpha Centauri is 40 trillion kilometers from Earth. At the Apollo 10 speed, reaching the nearest star would take approximately 114,000 years. Sit with that. Not as a metaphor, as a measurement. 114,000 years. The entirety of recorded human history is about 5,000 years. The nearest star is 22 recorded human histories away, at the fastest speed anyone has ever travelled. This is where tonight begins. The solar system, in other words, is not a destination we have visited. It is a neighbourhood we have barely left the front porch of. The heliopause, where the sun's wind gives way to interstellar space, is roughly 3 times, further than what the human speed record could reach in a lifetime. The nearest star is 6,500 times further than what the Apollo 10 speed can reach in 80 years. These are not pessimistic interpretations of the numbers. They are the numbers. They are where we start tonight, with the honest baseline before the better options enter the picture. To travel to the stars in a human lifetime, you need to go faster. Much faster. The question of how much faster is answered by arithmetic that is simple in principle and vertiginous in practice. A human lifetime of 80 years at the speed of light would cover 80 light-years of distance. That is, by galactic standards, barely a step outside the front door. The Milky Way is about 100,000 light-years across. The centre of the galaxy is 26,000 light-years away. The nearest large galaxy, Andromeda, is 2.5 million light-years away. Even at the speed of a light, a human lifetime is not enough to reach more than a tiny neighbourhood of nearby stars. But the speed of light is the upper limit. Nothing with mass can reach it. The faster you go, the more energy it takes to go faster still. The energy requirement grows without bound as you approach light speed. You can approach it. You cannot reach it. This is not a technological limitation. It is a law of physics that appears to be genuinely absolute. So the question becomes, what fraction of the speed of light is achievable? With what technology? And what does that buy you in terms of lifetime travel distance? To reach Proxima Centauri, the closest individual star at 4.24 light-years, in a 40-year journey, you need to average about 10% of the speed of light, 30,000 kilometers per second. That is about 108 million kilometers per hour, about 2,700 times faster than the Apollo 10 speed record. To reach the centre of the galaxy in a 50-year journey, you need to average more than 500 times the speed of light as measured by Earth time. That is impossible under any known physics. But if you allow the strange accounting of relativity, the answer changes. And it changes in a way that is one of the most astonishing results in all of physics. More on that shortly. First, the rockets. The reason to establish the speed needed before discussing the engines is that it clarifies what the engineering problem actually is. It is not a problem of ambition or vision or funding in the first instance. It is a problem of exhaust velocity, of energy density, of the ratio of fuel mass to payload mass that the rocket equation imposes on anyone trying to reach a significant fraction of the speed of light. Understanding the target speed is understanding the size of the problem. The problem is large. The physics does not make it small just because we would prefer it to be small. But the physics also does not make it impossible. That distinction is the entire subject of tonight. A rocket works by throwing mass out the back. This is Newton's third law, applied at high speed. The faster you can throw the exhaust, and the more exhaust you have, the faster you go. The relationship between exhaust velocity, fuel mass, and final velocity is captured by the Tsiolkovsky rocket equation, derived in 1903 by a Russian schoolteacher who never built a single rocket but who understood, with mathematical precision, what it would take to leave Earth. The rocket equation has an ugly implication for interstellar travel. To go faster, you need more fuel. But more fuel means more mass. More mass means you need even more fuel to accelerate that mass. The fuel requirement grows exponentially with the desired final velocity. For a chemical rocket which exhausts gases at a few kilometers per second, Reaching even 1% of the speed of light requires a fuel-to-payload ratio so large that the spacecraft itself would be a negligible fraction of the total mass at launch. The fuel would outweigh the payload by a factor of thousands of millions. Chemical rockets cannot reach the stars in any human time frame. This is not a matter of cost or engineering, it is arithmetic. The way forward is to exhaust your reaction mass faster. The faster the exhaust, the less of it you need. Nuclear thermal rockets, which use a nuclear reactor to heat propellant to higher temperatures than any chemical reaction can achieve, can produce exhaust velocities several times higher than chemical rockets. They have been tested. Project Nerva, run by NASA and the Atomic Energy Commission in the 1960s, demonstrated a working nuclear thermal rocket engine. Nuclear thermal can get you to Mars faster, significantly faster. It cannot get you to the stars in a lifetime. Nuclear pulse propulsion is different in kind, not degree. Project Orion, studied seriously in the late 1950s and 1960s by Freeman Dyson and others, proposed a spacecraft that would detonate nuclear bombs behind a massive pusher plate and ride the shock waves. The exhaust velocity of a nuclear explosion is many times higher than any chemical or thermal process. Theoretical Orion designs reached projected velocities of several percent of the speed of light. A spacecraft launched by nuclear pulse, under the most optimistic engineering assumptions, might reach Proxima Centauri in a few hundred years, still not a lifetime, but getting closer to the right order of magnitude. The key insight from all of this is that the exhaust velocity is the hard constraint. You need to throw something out the back as fast as possible. The fastest thing you can throw is light itself. The exhaust velocity is the fundamental number. Everything else follows from it. Chemical rockets exhaust gases at a few kilometers per second. Nuclear thermal rockets can reach perhaps 8 to 10 kilometers per second. Ion drives can reach 50 to 100 kilometers per second, but at very low thrust. Nuclear pulse drives using bomb propulsion could reach thousands of kilometers per second. The matter-antimatter drive exhausts photons at the speed of light, 300,000 kilometers per second. Each step up the exhaust velocity ladder opens more of the solar system, and eventually the stars. The ladder goes high. We are near the bottom rung. The question is, how much of the ladder can be climbed in the time available? If you could convert mass entirely to energy, and direct that energy as exhaust, you would have a photon rocket. This is the theoretical upper limit of rocket performance under known physics. The exhaust velocity would be the speed of light. No rocket can do better than this, because nothing travels faster than light. A photon rocket with perfect conversion efficiency could, in principle, accelerate a spacecraft to a substantial fraction of the speed of light, with a fuel mass that, while large, is not astronomically unreasonable. The closest real-world approximation to this ideal is matter-antimatter annihilation. When a particle of matter meets its antiparticle, both are converted entirely to energy. The conversion efficiency is 100%. No chemical reaction, no nuclear reaction, nothing else we know of converts mass to energy with this completeness. A matter-antimatter rocket, if built, would be the most efficient propulsion system physically possible. The exhaust would be high-energy gamma rays and other particles moving at or near the speed of light. The fuel-to-payload ratio for a round trip to Proxima Centauri, accelerating at 1 gravity for the first half and decelerating at 1 gravity for the second half, would be roughly 40 kilograms of antimatter fuel for every kilogram of payload. Large, but not infinite. The problem, of course, is that antimatter barely exists in nature and is extraordinarily difficult and expensive to produce artificially. The entire cumulative output of all antimatter production at CERN in the history of the institution amounts to a few nanograms. At current production rates, producing the fuel for even the smallest imaginable interstellar mission would take longer than the age of the universe. And storing antimatter is its own engineering challenge, since it annihilates on contact with any normal matter container. But the photon rocket, the antimatter drive, matters for our conversation not as a near-term engineering proposal, but as a bound. It tells us the best case, the maximum speed achievable under known physics with a rocket that carries its fuel, and the maximum speed, with a fuel ratio of 40:1, is large enough to reach the nearest stars in a human lifetime if the antimatter problem could somehow be solved. This is what a lifetime of travel can buy you, in principle, under the laws of physics we know. Not in practice, not soon. But in principle, under those laws, a human lifetime is not obviously insufficient for interstellar travel. Physics does not forbid it. Engineering and chemistry do for now. The antimatter problem is not a problem of concept. The concept is clear. It is a problem of production. Antimatter is produced in particle accelerators when enough energy is concentrated in a small enough space to produce particle-antiparticle pairs. The process is inefficient. For every unit of energy used to produce antimatter, less than a billionth of that energy ends up stored in the antimatter produced. At current production rates, fueling even a small interstellar mission with antimatter would require the entire energy output of civilization for billions of years. This is not a near-term engineering problem. It is a fundamental constraint on how much antimatter the universe is willing to give us per unit of energy invested. Whether that constraint can be circumvented with better technology is unknown. In 1905, Albert Einstein published a paper that changed the relationship between motion and time in a way that most people still do not fully absorb, even people who know the result. Moving clocks run slow, not metaphorically, not approximately, literally. A clock that is moving relative to an observer ticks more slowly than a clock that is stationary relative to that observer. This is not an artifact of the clock's mechanism. It is a property of time itself. Time passes more slowly for moving objects than for stationary ones, and the effect becomes dramatic as the speed approaches the speed of light. This is called time dilation. It is experimentally verified to high precision. GPS satellites run fast by about 38 microseconds per day, relative to clocks on the ground, due to a combination of time dilation from their velocity and the opposing effect from their weaker gravitational field. Without corrections for these relativistic effects, GPS systems would accumulate positioning errors of about 10 kilometers per day. The corrections are applied constantly. They work. Special and general relativity are not speculation. They are the foundation of navigation technology used billions of times per day. The formula for time dilation involves a quantity called the Lorentz factor, gamma. At 10% of the speed of light, gamma is about 1.005. Time passes about 0.5% slower on the moving spacecraft than on Earth. Negligible. At 50% of light speed, gamma is about 1.15. Time passes about 15% slower. At 86% of light speed, gamma is 2. Time passes twice as slowly on the spacecraft. At 99% of light speed, gamma is about 7. For every year that passes on the spacecraft, 7 years pass on Earth. At 99.99% of light speed, gamma is about 71. For every year on the spacecraft, 71 years pass on Earth. At 99.9999%, gamma is about 707. The implications of this for the question of how far a human can travel in a lifetime are, once you let them land, genuinely shocking. Because the question has two answers, depending on whose clock you are using. The answer measured in Earth time is one thing. The answer measured in the traveller's own biological time is something else entirely. These two answers diverge spectacularly as the speed approaches light. The practical implications of time dilation for interstellar travel are extraordinary and underappreciated. The word relativistic, applied to a spacecraft's speed, usually just means fast. But fast enough for time dilation to matter is fast enough to change the relationship between the traveller and the universe they left. At 10% of light speed, the effect is tiny. At 50% significant. At 90% profound. At 99.99% transformative. The traveller ages years while the universe ages centuries or millennia. The stars ahead have moved slightly in the sky by the time the traveller arrives, because years of light travel time have elapsed for those stars even as the traveller experiences only a compressed version of that interval. The physics of time is not an abstraction at these speeds, it is the operating environment. Here is the calculation that changes everything. A spacecraft accelerating at 1 gravity, 1 g, the same gravitational acceleration you feel sitting in your chair right now, provides a comfortable and physiologically manageable experience for its crew. No weightlessness, no bone loss, no cardiovascular deconditioning. The crew lives in an environment that feels, physically, like standing on Earth. They age normally. Their bodies function normally. Their clocks tick at the normal rate relative to themselves. Now accelerate that spacecraft at 1 g continuously. How fast do you get? After 1 year of ship time, you are moving at about 77% of the speed of light. After 2 years, about 97%. After 3 years, about 99.5%. The speed approaches light asymptotically, getting closer and closer but never reaching it, while the Lorentz factor climbs without bound. Here is what that buys you in terms of distance covered as measured by Earth frame coordinates. The distances between stars as we measure them with telescopes, while the crew ages only according to their own biological clock. Proxima Centauri, 4.24 light-years away, reachable in about 3.6 years of ship time with constant 1 g acceleration and deceleration. The crew ages 3.6 years, Earth time elapsed, about 6 years. The centre of the Milky Way, 26,000 light-years away, reachable in about 20 years of ship time. The crew ages 20 years. Earth time elapsed, about 26,000 years. The Andromeda Galaxy, 2.5 million light-years away, reachable in about 29 years of ship time. The crew ages 29 years. Earth time elapsed, 2.5 million years. The observable universe, roughly 46 billion light-years in radius, reachable in about 46 years of ship time. The crew ages 46 years. Earth time elapsed, 46 billion years, more than 3 times the current age of the universe. Read those numbers again. A crew that left Earth at age 25 under continuous 1 g acceleration and deceleration could reach the edge of the observable universe before their 71st birthday. The universe itself ages by more than 3 times its current age during the trip. Everything they knew on Earth would be gone. Every star would have burned out. But they would arrive. This is not science fiction. This is the mathematical consequence of special relativity applied to constant acceleration. The equations are settled physics. The only question is the engine. The 1 g calculation is worth repeating, because the numbers are so counterintuitive that they tend to be dismissed as impossible even by people who understand the physics. They are not impossible. They are correct. The Lorentz factor at 99.9999% of light speed is about 707. For every year the crew ages, 707 years pass outside the ship. A crew that accelerates and decelerates at 1 g for a total of 46 years of ship time covers a distance of roughly 46 billion light-years in Earth frame coordinates. The observable universe is about 46 billion light-years in radius. The math is not subtle. The physics really does say that a human lifetime is sufficient to cross everything we can see, given the engine. The engine is the problem. The destination is not. The engine required for a 1G continuous acceleration spacecraft is, to put it plainly, nothing we have or are close to having. The energy required to accelerate a spacecraft at 1G for years is staggering by any scale of current human energy production. Consider a spacecraft with a mass of 1,000 metric tons, roughly the mass of the International Space Station. To accelerate this at 1G using a perfect matter-antimatter photon drive, the fuel consumption rate is roughly 30 kilograms of antimatter per day in the initial phases, increasing as the ship gains mass-equivalent energy at relativistic speeds. Over a 10-year journey, the total fuel mass required would be comparable to the mass of a large asteroid. The entire mass energy of the fuel would need to be converted to thrust with perfect efficiency. This is not an engineering challenge in the conventional sense. It is several engineering challenges simultaneously, each one beyond current capability by many orders of magnitude. Producing antimatter at scale, storing it without annihilation, converting its energy to directed thrust efficiently, surviving the radiation environment created by the annihilation, building a structure that can maintain structural integrity under continuous acceleration at these energies for years. So the 1G antimatter drive is a bound, a theoretical maximum performance, not a near-term blueprint. What can actually be built? Project Daedalus, a serious engineering study conducted by the British Interplanetary Society in the 1970s, designed a two-stage fusion rocket intended to reach Barnard's star, about 6 light-years away, in 50 years. The design used inertial confinement fusion, igniting tiny pellets of deuterium and helium-3 at a rate of 250 per second to produce thrust. The projected terminal velocity was about 12% of the speed of light. The design was not a spacecraft you could build today, but it used no exotic physics. Every component was based on principles that were understood in the 1970s, if not yet achievable in hardware. At 12% of the speed of light, a human lifetime of 80 years covers about 9.6 light-years in ship time, with modest relativistic effects at that speed. That is enough to reach a handful of nearby stars, not to cross the galaxy, not to reach Andromeda, but to step outside the solar system and stand on alien ground, if any of the nearby stars have ground worth standing on. This is what serious 1970s engineering could sketch out. Half a century later, we are not closer to building it. The 1G antimatter drive is not the only path. It is the performance upper bound for a rocket that carries its fuel. Other approaches, laser sails, ramjets, beamed energy, take different positions on the trade space between performance and buildability. The antimatter drive is the best performing and the least buildable. Laser sails are the least performing at crude mass scales and potentially the most near-term. The generation ship is performance agnostic, solving the lifetime problem by extending the mission across multiple lifetimes rather than compressing the journey time. Each approach has a different relationship to the question of what a human lifetime can accomplish. The antimatter drive makes the lifetime irrelevant by making the journey short enough. The generation ship makes the journey possible by making the lifetime irrelevant. The laser sail makes the journey possible for probes, but not yet for people. The energy problem is the central problem of interstellar travel, and it has no solution that does not involve either enormous fuel masses or energy sources that do not yet exist at relevant scales. Here is a way to feel the size of the problem. The kinetic energy of a 100,000-ton spacecraft moving at 10% of the speed of light is approximately 4.5 times 10 to the power of 22 joules. That is about 10,000 times the total annual energy consumption of human civilization. All the power plants, all the cars, all the burning of all the fossil fuels, all the renewables, everything humanity uses in a year, times 10,000, for a single spacecraft moving at 1/10 of light speed. At 50% of light speed, the kinetic energy is about 15 times higher still. Current human civilization generates about 1.5 times 10 to the power of 13 watts of power on average. To accelerate a 100,000-ton spacecraft to 10% of light speed in 1 year would require a power source several billion times more powerful than the entire current output of human civilization, sustained for a year. This is not a funding problem. It is a physics and engineering problem. The energy has to come from somewhere. It has to be stored or generated on board or transmitted from outside. No current or near-future technology provides it. But there is a different approach that sidesteps the fuel problem entirely. Instead of pushing the spacecraft from behind, you push it from a distance. Instead of carrying the energy source on the spacecraft, you leave it at home and beam the energy outward. This is the laser sail concept, and it is the most credible near-term proposal for achieving interstellar velocities that currently exists. A thin reflective sail, pushed by an enormous laser or array of lasers, can be accelerated to a significant fraction of the speed of light without carrying any propellant at all. The energy source stays on Earth or in orbit. The spacecraft is just a sail and a payload. The lighter the payload, the faster you can push it. The Breakthrough Starshot initiative, announced in 2016 and funded with an initial $100 million, is pursuing exactly this idea. Not for crude spacecraft. For gram-scale probes, tiny wafers of electronics and sensors, accelerated to 20% of light speed by a ground-based laser array. At that speed, the journey to Alpha Centauri takes about 20 years. Gram-scale probes are not people, but the physics is real and it is happening. The energy comparison to civilizational output is not meant to discourage, it is meant to calibrate. The Wright brothers flew for 12 seconds in 1903. 66 years later, humans walked on the moon. That is a factor of roughly 10 million in performance improvement in 66 years. Aviation and rocketry did not achieve this by a gradual, predictable accumulation of small improvements. They achieved it through a combination of theoretical breakthroughs, engineering ingenuity, and the specific pressures of competition and urgency. The history of technology does not suggest that a factor of 1 billion in energy availability is permanently out of reach. It suggests that the timescale and the motivation determine when it happens, not the magnitude of the improvement. Breakthrough. Starshot is worth understanding in some detail because it is the only currently funded, actively researched program aimed at achieving interstellar velocities in the near term. The concept is this: a laser array on the ground with a combined power of somewhere between 50 and 100 gigawatts focuses its beam on a sail roughly 4 meters across, made of a material perhaps a few hundred atoms thick. The sail and its attached probe chip, together weighing about 1 gram, are in orbit. The laser fires for a few minutes. The sail accelerates to 20% of the speed of light. The probe coasts for 20 years to Alpha Centauri, flies through the system, photographs whatever planets it finds, and transmits the images back to Earth using its onboard laser. The transmission takes 4.24 years to arrive. The engineering challenges are extraordinary. A 100 gigawatt laser array is roughly 50 times more powerful than any laser ever built. The sail material must reflect more than 99.99% of the laser energy, or it will be destroyed by the fraction it absorbs. The pointing accuracy required to keep the beam on a 4-meter sail accelerating away at 20% of light speed in real time, accounting for atmospheric effects, and mechanical tolerances, is at the edge of what appears physically possible. The probe electronics must survive the radiation environment of interstellar space for 20 years on power generated by a sail the size of a large book. None of these problems is solved. All of them are being actively worked on. The Breakthrough Starshot team, which includes some of the most respected names in physics and engineering, believes they are all solvable in principle. A demonstration mission, a smaller version of the full concept, might be possible within this century. What Starshot would send to Alpha Centauri is not a person. It is a chip with a camera and a laser. The probe has no life support, no propulsion, no way to slow down or enter orbit. It will fly through the Alpha Centauri system in hours, photographing frantically, then continue out the other side into the dark. But it would be the first human artifact to reach another star system. Not a human, a probe. But the probe would tell us what is there. And knowing what is there is the prerequisite for deciding whether to send something that can stay. The Starshot program has clarified the problem in ways that were not previously well understood, by forcing a specific and technically honest examination of what each component needs to do. The laser array power requirement, the sail material reflectivity requirement, the pointing accuracy requirement, the probe miniaturization requirement. All of these have been analyzed to engineering level detail, not conceptual level detail. The result is a clearer picture of where the hard problems actually are, which turns out to be different from where people assumed the hard problems were before the analysis was done. This is the value of a serious program, not that it builds the thing, that it finds out honestly what building the thing actually requires. There is another approach to interstellar travel in a human lifetime that does not depend on going fast at all. It depends on living long. A generation ship is a spacecraft large enough, complex enough, and self-sufficient enough to sustain a human community for the entire duration of a journey measured in centuries or millennia. The people who leave Earth are not the people who arrive. Their great-grandchildren arrive, or their 10th generation descendants. The ship is the world. The destination is a legacy. The idea was proposed seriously in the 1920s and has been studied with increasing rigour since. The engineering requirements are understood well enough to say that a generation ship is not physically impossible. It would require a closed-loop life support system of extraordinary reliability. It would require a genetic population large enough to avoid inbreeding depression over many generations, generally estimated at several hundred to a few thousand founding individuals. It would require a social and cultural structure capable of maintaining purpose and cohesion across timescales that make any existing human institution look brief. At 1% of the speed of light, a speed achievable with sufficiently advanced nuclear propulsion, the journey to Alpha Centauri takes about 430 years. That is roughly the time between Columbus reaching the Americas and today. Many generations. The people who depart have no direct connection to the people who arrive except through culture and biology, and the accumulated memory of the ship's library. At 5% of the speed of light, the journey takes about 85 years. Possible, barely, in a single extended lifetime. At 10%, about 42 years, a single human generation. The question of what speed is achievable is, again, the question of the engine. But the generation ship sidesteps the need for relativistic speeds entirely. It does not require exotic physics or fuel ratios that strain credulity. It requires engineering that is understood in principle and social engineering that is understood only in theory. It might be the most buildable of the interstellar concepts, even if it is the most demanding in terms of sustained human commitment. The problem is that it requires every generation born on the ship to accept a role they did not choose, to live their entire lives in service of a destination they will never see, to maintain a civilization in a metal can for centuries without external contact or the option to quit. No human society has ever voluntarily sustained itself under these conditions. The generation ship is as much a sociology problem as an engineering problem, possibly more so. The generation ship is, in some ways, the most human of the interstellar proposals, because it does not require the physics to be different from what it is. It requires the engineering to be excellent and the social organisation to be sustained. Both of these are things humans have done before, at smaller scales and shorter timescales, but the pattern is recognisable. A community maintaining itself in an isolated environment, passing its purpose to its children, reaching a destination that its founders chose but never saw. Human history has examples of something close to this, in cultures that maintained traditions and purposes across many generations in the face of a hostile or indifferent environments. The generation ship is that at an extreme of scale and duration. Whether the human capacity for multi-generational purpose can be maintained for the centuries or millennia of an interstellar voyage is an empirical question that has not been tested. The nearest confirmed exoplanet system is Alpha Centauri. The nearest confirmed potentially habitable exoplanet orbiting in the habitable zone of its star is Proxima Centauri b, discovered in 2016, orbiting Proxima Centauri at a distance that puts it within the range where liquid water could theoretically exist on its surface. Proxima Centauri is a red dwarf, a small, dim, active star that flares frequently with bursts of X-ray and ultraviolet radiation. Whether Proxima b has an atmosphere, whether it has retained any water, whether the habitable zone of a flare star is actually habitable, these questions are not yet answered. The planet was detected via the radial velocity method, which measures the tiny wobble the planet induces in the star's motion. We know its minimum mass is about 1.07 times Earth's mass, and we know its orbital period is about 11.2 days. We know almost nothing else. The extremely large telescope, currently under construction in Chile and expected to achieve first light in the late 2020s, should be able to directly image Proxima b and potentially analyse its atmosphere through transit spectroscopy. Within the next decade, we may know whether Proxima b has an oxygen-rich atmosphere, or a CO2 greenhouse, or nothing at all. We may know whether it has water. We will probably not know whether it has life. But Proxima b matters for the question of this video because it is 4.24 light-years away, and it might be habitable. It is the nearest possible destination that is not just a rock in hard vacuum. It is a candidate. The first candidate, the one you would put at the top of the list if you were designing an interstellar mission and needed to pick a target. 4.24 light-years at 20% of the speed of a light, Starshot speed, is a 21-year journey. But Starshot sends gram-scale probes. A crewed mission at 20% of light speed, if such a thing were possible, would reach Proxima b in 21 years of Earth time, or about 20.8 years of ship time at that speed, within a human lifetime, if you left young enough, and if the mission were one way. One way. That word carries enormous weight. One way means you're not coming back. You're not visiting. You're leaving. You're the last of your kind to ever see the Earth from the ground, and the first of your kind to see Proxima b from orbit. The question of whether any human being would make that trade is not a physics question. It is a deeply human one. The interest in Proxima b is not purely scientific, it is also strategic. In the practical planning of any future interstellar mission, the destination needs to be worth the cost and the risk. A star system with no planets is a destination with nothing to offer beyond the scientific knowledge that the journey itself provides. A star system with a potentially habitable planet is a destination with everything to offer, including the possibility that the mission could be self-sustaining, that the travellers could establish a permanent presence, rather than simply pass through. Proxima b is not confirmed habitable, but it is the closest candidate. The investment in characterizing it before any mission is launched is the obvious first step in a very long planning process. Let us be specific about what the relativistic time dilation actually means for the traveller, because the numbers are so strange that they tend to slide off the mind without fully registering. A crew of 20 people leaves Earth at age 30. Their spacecraft accelerates at 1 g for the first half of the journey to the Andromeda Galaxy, and decelerates at 1 g for the second half. The journey covers 2.5 million light-years in Earth frame distance. From Earth's perspective, the journey takes about 2.5 million years. From the crew's perspective, measured by their own heartbeats and aging, it takes about 29 years. They arrive in Andromeda at age 59, still working age, potentially still capable of establishing whatever settlement they plan to establish, if the destination turned out to be suitable. Meanwhile, on Earth, 2.5 million years have passed. The humans who launched the mission are not just dead. Their entire civilization, every institution, every language, every cultural reference point the crew shares, is gone. The species that built the spacecraft may no longer exist in recognizable form. The Sun has moved a significant fraction of a full orbit around the galactic center. The night sky, as seen from Earth, looks different because the nearby stars have drifted relative to each other over 2.5 million years. The crew arrives at Andromeda with their memories of Earth intact, their bodies still young, their training still relevant, their cultural identity still that of the civilization that launched them. But there is no civilization behind them anymore. No signal from Earth can reach them faster than 2.5 million years. No help is coming. No supply ship is following. Whatever they find in Andromeda, they find alone. This is not a scenario for which human psychology was designed. The deepest human social instincts are calibrated for small groups, for communication with home bases, for the option of return. A crew arriving at Andromeda 2.5 million years after departure is not psychologically returning from a voyage. They are the beginning of something else. The last connection to Earth is the memory of a planet that no longer exists as they knew it. The mathematics of relativistic travel does not just compress the journey, it severs the connection to home in a way that is absolute and final. You can go anywhere in the observable universe in one biological lifetime. You can never come back to the world you left. The psychology of the arrival scenario is the part of relativistic interstellar travel that gets least attention and most deserves it. The physics of time dilation has been analysed in detail. The engineering challenges have been studied seriously. The psychology of a crew arriving at a destination 2.5 million years after departure, to a galaxy where everything they knew is extinct, has been studied much less rigorously. The closest analogue in human experience is perhaps the experience of a survivor of an isolated catastrophe, someone who has lost everything familiar and must build a new life in an alien environment with whatever resources they have. But even that analogue understates the isolation. The crew arriving at Andromeda is not just isolated from people they knew. They are isolated from the entire historical context that gave their civilization meaning. They must create meaning from scratch, with only each other and the destination. The Fermi paradox is the name given to the observation, made by physicist Enrico Fermi over lunch in 1950, that the universe is old enough and large enough that if interstellar travel is possible, at least some civilization should have had time to colonize the entire galaxy, and yet we see no evidence of any civilization having done so. The galaxy is about 100,000 light-years across. The Milky Way has been forming stars for about 13 billion years. If a civilization developed interstellar travel 5 billion years ago, and expanded outward at even 1,000th of the speed of light, it could have colonized the entire galaxy in about 100 million years, 1% of the time available. The galaxy could have been settled and resettled many times over in the age of the universe, and yet, no alien signals detected, no alien artifacts found, no Dyson spheres visible in stellar surveys, no evidence anywhere of intelligence having done what the math suggests should have been done by now. One resolution to the Fermi paradox that is relevant tonight is the difficulty hypothesis. Maybe interstellar travel is simply harder than the math suggests. Maybe the energy requirements, the engineering challenges, the social and psychological demands, the sheer span of time required even at relativistic speeds constitute a filter that most civilizations cannot pass. Not because the physics forbids it, because the technology required is so far beyond the early industrial stage that most civilizations fail or stagnate before reaching it. Another resolution is the distance hypothesis. Maybe the galaxy has been colonized, but the distances are so large and the travel time so long that the civilizations are so spread out as to be effectively undetectable to each other. Maybe there are 1 million civilizations in the Milky Way and they're all so far apart, and the signals between them so old by the time they arrive that the galaxy looks silent from any one vantage point. A third resolution is darker. Maybe interstellar travel is possible, but something eliminates civilizations before they can attempt it. What that something is, whether it is internal self-destruction or some external catastrophe, is the subject of the great silence at the heart of the Fermi paradox. Tonight's question, how far can humans travel in a lifetime, connects directly to whether any answer to the Fermi paradox is actually correct. If the physics allows it, if the engineering could be achieved, if the social and psychological challenges could be managed, then the human answer to Fermi is, eventually, we go. What happens after that is the rest of the story. The Fermi paradox has a specific application to tonight's question that is worth making explicit. If the physics allows interstellar travel in a lifetime, and if there are many civilizations in the galaxy, then either most civilizations choose not to expand, or most civilizations are eliminated before they can expand, or the physics is harder than it appears, or the galaxy has been expanded into, and we have not recognized the evidence. Each of these options has different implications for human interstellar ambition. If most civilizations choose not to expand, the decision is genuinely open, and humans could choose differently. If most civilizations are eliminated before expanding, the urgency of interstellar expansion is exactly as high as the threat level suggests. If the physics is harder than it appears, the timeline for human interstellar travel extends accordingly. The Fermi paradox is not a pessimistic argument. It is a question about which of several possible realities we inhabit. There is a proposal that sidesteps the propulsion problem by taking a different approach to the fuel. Instead of carrying fuel, harvest it from space as you go. The Bussard ramjet was proposed by physicist Robert Bussard in 1960. The concept is elegant. Interstellar space is not quite empty. It contains hydrogen at densities of about 1 atom per cubic centimetre in the regions between stars. Hydrogen is fusion fuel. If a spacecraft could scoop up this interstellar hydrogen and fuse it in a thermonuclear reactor, it could in principle accelerate indefinitely without carrying any fuel at all. The fuel is the medium it moves through. The engineering requires a magnetic scoop of enormous dimensions, perhaps hundreds of kilometers across, to gather enough hydrogen at any reasonable velocity to sustain fusion. The spacecraft itself would be far smaller. The scoop would be a field, not a physical structure. As the spacecraft accelerated, the scoop would need to gather faster. but the hydrogen density in its path would also increase from the spacecraft's perspective due to length contraction, helping balance the equation. If the Bussard ramjet worked, the implications for the lifetime travel question would be transformative. With an essentially unlimited fuel supply, a spacecraft could accelerate at 1G indefinitely. The crew would age normally. The destinations would be unlimited. The entire observable universe would be accessible in a human lifetime. There are unfortunately serious problems with the concept. The proton-proton fusion reaction used in the Sun requires temperatures and confinement times that are difficult to achieve in a ramjet configuration. More importantly, the drag from scooping the interstellar medium may exceed the thrust generated by fusing it, meaning the ramjet decelerates rather than accelerates. Detailed calculations done in the 1970s cast serious doubt on whether the device works as a propulsion system in any realistic configuration. But the concept remains interesting as a direction of inquiry. Whether a different scoop geometry, a different fusion reaction, or a different approach to the basic idea of harvesting propellant from the medium could work is not definitively settled. The Bussard ramjet probably does not work as originally proposed. The underlying question, can you fuel an interstellar journey from interstellar space itself, is still open. The Bussard ramjet failure mode is instructive for understanding propulsion proposals more generally. The concept was compelling in theory, elegant in its use of existing interstellar resources, and turned out to have practical obstacles that were not apparent from the original theoretical analysis. The lesson is not that fusion ramjets are impossible. It is that any propulsion concept proposed at the theoretical level needs detailed analysis to reveal the engineering and physics obstacles that are not visible from the conceptual level. The history of advanced propulsion is full of concepts that were compelling in theory and either failed in practice or required significant modification to be viable. The ramjet is one. The Orion nuclear pulse drive worked in principle, but was politically unacceptable in practice. Ion drives work, but with thrust levels that make them impractical for crewed interstellar missions at any near-term scale. The gap between concept and hardware is where most propulsion ideas fail. There is a concept in general relativity, Einstein's theory of gravity, that is mathematically valid under known physics, and that, if physically realizable, would change the answer to tonight's question completely. It is called the Alcubierre drive, proposed by Mexican physicist Miguel Alcubierre in 1994. The idea starts from something counterintuitive but real. Space itself can move. The expansion of the universe is space expanding, not galaxies moving through space. Distant galaxies are not moving away from us. The space between us and them is growing. This is a genuine physical effect, confirmed by observation. Space is not a static backdrop. It is a dynamic medium that can stretch, compress, and curve. Alcubierre proposed that it might be possible to create a localized distortion of space-time, contracting space in front of a spacecraft and expanding it behind, creating a bubble in which the spacecraft would be at rest while the bubble itself moved through space at any desired speed, including faster than light. Inside the bubble, no, local physics would be violated. The spacecraft would not be moving through space. Space would be moving around it. The practical problems are severe. The energy required to create and maintain an Alcubierre bubble, by original calculations, was comparable to the mass energy of Jupiter. Later refinements reduced the estimate, but the energy requirements remain at scales that are not approachable by any imaginable near-term technology. More fundamentally, it is not clear that the exotic matter required to create the negative energy density needed for the bubble actually exists, or that the laws of physics permit it to exist in the required form. But the Alcubierre drive matters for tonight's conversation because it illustrates something important. The question of whether faster-than-light travel is possible is not answered by special relativity. Special relativity says you cannot accelerate a massive object to the speed of light. It does not say you cannot move between 2 points faster than light would travel between them through static space, if space itself is the thing moving. Whether this loophole in the physics is actually exploitable, whether the universe permits the energy conditions and matter configurations required, is genuinely unknown. We do not know that the Alcubierre drive is impossible. We know it is not currently achievable, and that its requirements appear to involve physics we do not have. That is a different statement. The Alcubierre metric is a precise mathematical solution to Einstein's equations. Not an approximation, not a speculation, a solution. Einstein's field equations admit many solutions, most of which correspond to physical scenarios we can observe, but some of which correspond to geometric configurations that may or may not be physically realizable. Black holes were solutions to Einstein's equations long before they were confirmed to exist. Gravitational waves were solutions long before they were detected. The fact that something is a solution to Einstein's equations is not proof that it exists in the physical universe, but it is significant evidence that the laws of physics do not trivially exclude it. The Alcubierre drive is in this category, not confirmed, not excluded, requiring physics we do not have, but present in the mathematics of the most successful theory of gravity we possess. There is another shortcut through the fabric of space-time that general relativity permits in theory, and it has been part of the landscape of theoretical physics since Einstein and Nathan Rosen described it in 1935. A wormhole, or Einstein-Rosen bridge, is a tunnel through space-time connecting two distant regions. In principle, a wormhole could connect 2 points billions of light-years apart, allowing travel between them in a negligible time, measured either by Earth clocks or the traveller's clock. Real wormholes, if they exist, are thought to be microscopic, formed and destroyed in quantum foam at scales far smaller than an atomic nucleus. They have never been observed. Creating a stable, traversable wormhole large enough for a spacecraft and keeping it open against its natural tendency to pinch off would require vast quantities of exotic matter with negative energy density. This same problematic ingredient as the Alcubierre drive. But the theoretical status of wormholes is interesting in a specific way. Unlike perpetual motion machines or faster-than-light particles, wormholes are not ruled out by any known law of physics. They are solutions to the equations of general relativity. The equations that describe the bending of space-time around massive objects, confirmed to extraordinary precision by every test we have applied, also describe wormholes as valid geometric configurations. The physics permits them. Whether the physics also permits the conditions needed to create or stabilize them is a separate question. Kip Thorne, who won the Nobel Prize for his work on gravitational waves, studied traversable wormholes seriously in the 1980s and concluded that they were not forbidden by known physics, but that stabilizing them would require exotic matter whose existence is uncertain. His work was part of a broader program of understanding what general relativity actually permits versus what it predicts will happen under natural conditions. The honest assessment of wormholes in 2024 is that they are not engineering proposals, not near-term science projects, and not things that any currently imagined technology could create. They are instead the universe's answer to the question of whether faster-than-light travel is geometrically possible, and the answer, according to general relativity, is yes in principle. Whether nature permits the conditions needed to build one is not yet settled. For tonight's question, wormholes represent the extreme end of the possibility space, not what we can do, what the universe might, under the right conditions, allow. The wormhole concept has been taken seriously enough by physicists to be the subject of a Nobel lecture by Kip Thorne, serious papers in physical review letters, and an entire subfield of quantum gravity research centered on the ER equals EPR conjecture, which proposes a deep connection between wormholes in general relativity and quantum entanglement in quantum mechanics. Whether this connection could ever be exploited for information or matter transmission is unknown, but the fact that wormholes appear in both the classical theory of gravity and the quantum theory of information suggests that they are not just mathematical curiosities. They are at minimum something the universe is structured to accommodate in its most fundamental descriptions. Let us come back to the present and to what is actually being worked on right now by people with funding and labs and engineers and a realistic hope of achieving results in the next few decades. The most credible near-term interstellar program is Breakthrough Starshot. We discussed the concept earlier. The engineering challenges are real, and none of them is solved. But the physics is understood, and the technology roadmap, while demanding, involves components that are continuous extensions of existing engineering rather than qualitative leaps into unknown territory. The laser array is the most demanding component. A 100 gigawatt laser in orbit requires advances in laser technology, power generation, and beam formation that are significant but not magical. The Defense Advanced Research Projects Agency and various national laboratories have been pushing laser technology for decades for reasons unrelated to interstellar travel. The trajectory of progress is not zero. The sail material is the component that may be closest to feasibility. Graphene and related two-dimensional materials discovered and characterized in the 2000s and 2010s have optical properties, strength-to-weight ratios, and thermal conductivities that make them plausible candidates for sail material. The fabrication of large, thin, uniform films of these materials is an active area of material science research. Not solved, not trivial, but not obviously impossible. The probe electronics are in some ways the most mature component. The miniaturization of sensors, cameras, computers, and communication lasers onto a chip-scale platform is a direction that silicon technology has been following for 50 years. A probe weighing 1 gram with a camera, a position sensor, a clock, and a communications laser is closer to today's technology than the laser array or the sail material. The combination of all three, integrated and tested and actually launched, remains far off. But Breakthrough Starshot, by committing serious money and serious scientists to the problem, has forced a more rigorous analysis of what is actually needed and what the genuine obstacles are. That analysis has clarified the problem in ways that were not previously understood. The answer to how far humans can travel in a lifetime is not, today, being worked out by people building spacecraft. It is being worked out by people figuring out what we would need to build spacecraft worth building. The most important thing Breakthrough Starshot has done is not technological. It has changed the conversation. Before Starshot, discussions of interstellar travel were largely confined to science fiction, speculative engineering papers in niche journals, and occasional optimistic assessments by futurists. After Starshot, there is a funded research program with real scientists attacking real technical problems with real money. The problems are hard. The solutions are not in hand, but the conversation has moved from whether to how, and that shift matters. It creates a community of researchers with a specific goal, a specific timeline, a specific set of technical challenges to solve. Communities with specific goals and specific timelines sometimes solve hard problems. The history of technology includes many examples: the Manhattan Project, the Apollo program, the Human Genome Project. The Starshot program is smaller than any of these, but it is in the same category of organized effort directed at a specific technical goal. There is a version of this question that does not involve traveling at all, at least not in the conventional sense. If you could transfer human consciousness, or the information content of a human mind, to a digital substrate and transmit that substrate as electromagnetic radiation at the speed of light, you could, in principle, travel between stars in years, not centuries, at essentially zero propellant cost. You would not travel in a spacecraft. You would travel as a signal. This idea, sometimes called uploading, mind transfer, or substrate-independent personhood, rests on an assumption that the information content of a human brain is what constitutes a person. That identity is not tied to biological substrate, but to pattern. If the pattern can be preserved and recreated, the person, in some meaningful sense, continues. The assumption is philosophically contested and empirically untested. Whether a reconstructed copy of a person's brain state is the same person, or just a copy, is a question that biology and physics cannot currently answer, because it depends on what we mean by the word person, a question that turns out to be much harder than it appears. But put the philosophy aside for a moment and consider the physics. Electromagnetic radiation travels at the speed of light. A signal sent from Earth to Proxima Centauri arrives in 4.24 years. If that signal encodes a human mind, and if a receiver at the other end can reconstruct that mind in a suitable substrate, the journey takes 4.24 years from both the sender's and receiver's perspective. No time dilation, no rocket fuel, no radiation damage to biological tissue, just the time it takes light to cross the distance. The information content of the human brain, measured in terms of synaptic connections, is estimated at roughly 100 to 1000 terabytes. Current cosmic ray transmission rates cannot accommodate this. Current reconstruction technology does not exist. The neuroscience required to accurately map and represent a human brain does not exist. The philosophical questions are not resolved. But as an upper bound on what is possible if the science develops, it is worth placing on the table. The physical limit on mind transmission speed is the speed of light. The physical limit on mind reconstruction is the fidelity of the map and the quality of the substrate. If both could be solved, the question of how far a human can travel in a lifetime has an answer that is bounded only by the observable universe. The philosophical question of whether a transmitted and reconstructed mind is the same person is not a question that can be answered by physics. Physics can tell you whether the transmission is lossless. Physics can tell you whether the reconstruction is accurate. Physics cannot tell you whether continuity of consciousness, the subjective thread of experience that each of us feels linking our past to our present, survives the interruption of transmission and reconstruction. This is the hard problem of consciousness applied to an extreme case, and the hard problem has no agreed solution in any less extreme case. What can be said is that if we ever develop the technology to transmit and reconstruct human mind, the people involved will almost certainly have strong opinions about whether the process preserves identity. Those opinions will be formed in the absence of definitive evidence, because the definitive evidence requires a perspective that only the reconstructed mind can provide. The relationship between time and distance in interstellar travel has an implication that does not get discussed enough, and it is not about physics. It is about psychology and culture, and the nature of what it means to belong somewhere. When the Polynesians crossed the Pacific in outrigger canoes 3,000 years ago, the journey between islands took weeks or months. They maintained contact with the places they had come from through return voyages, through trade, through shared cultural memory, through occasional meetings. Distance was great but not absolute. The connections were maintained across the water. When the first humans walked across the Bering Land Bridge into the Americas, perhaps 20,000 years ago, there was no return journey. The ice closed behind them. The contact was severed. But the distance was crossable in principle by their descendants, and the evolutionary and cultural divergence was gradual enough that when Europeans and American peoples encountered each other thousands of years later, they were recognizably the same species with overlapping biology and comparable cultural complexity. An interstellar voyage changes this equation completely. At the speeds available with realistic near-term technology, a one-way journey to Proxima Centauri takes decades to centuries. A round trip takes twice as long. The signal delay alone, the minimum time for a message to travel between the departure world and the destination, is 4.24 years each way. An 8-year round-trip minimum for a single exchange. For meaningful real-time communication or cultural exchange, the journey is functionally one way. This means that an interstellar mission, even a successful one, is not an extension of human civilization the way colonizing a new continent was. It is a severing. The people who go become something else, shaped by their journey and their destination in ways the home civilization cannot share. The people who stay become something else too, shaped by the absence and by the slow evolution of their own civilization over the years or centuries it takes for the colony to establish itself and send word back. The galaxy, if humanity were to spread across it over thousands of years, would not be a civilization. It would be a collection of civilizations, each descended from Earth, each evolved beyond recognition of the others, connected only by the faint thread of origin and the light-speed delay of messages that arrive years after they are sent. This is not a reason not to go. It is what going actually means. The historical analogies to permanent migration are imperfect but instructive. The Polynesian settlers of remote Pacific islands knew they were leaving permanently. The islands they had come from were reachable in principle, with the right weather and enough food and water for the return voyage, but many of the settlements they founded never returned. They built new societies in new places and maintained a connection to their origins through oral tradition, through navigational knowledge, through the objects they brought with them. Those connections were real and important even when the physical distance made regular contact impossible. An interstellar colony would maintain connections to Earth through radio transmissions, through transmitted cultural archives, through the genetic and cultural heritage of its founders. But the delay would make the connection asymmetric in ways that terrestrial migration never was. You can talk to Samoa from Fiji. You cannot have a real conversation with Earth from Proxima Centauri. There is a number that the physics of the solar system makes particularly important, and it sits just outside the reach of any current or near-future spacecraft. It is the distance from Earth to the heliopause, the boundary between the Sun's solar wind and interstellar space. About 120 astronomical units, about 18 billion kilometers, about twice the distance Voyager 1 has travelled in 47 years. Everything inside the heliopause is, in a meaningful physical sense, the Sun's neighbourhood. The Sun's magnetic field dominates. The Sun's wind of charged particles fills the space. The density of interstellar cosmic rays is reduced by the heliospheric shield. Going outside the heliopause means leaving the bubble the Sun blows around itself and entering the true interstellar medium. Voyager 1 crossed the heliopause in August 2012, after 35 years of travel. It was launched in 1977. The people who designed it are old or dead. The computers on board have less processing power than a modern wristwatch. It is transmitting on 23 watts of power. It is still transmitting, and it is the only human-made object we know of that has crossed into interstellar space. One object in 70 years of space travel. One object built by a civilization that has put 12 people on the moon and robots on Mars and telescopes in orbit that can see galaxies 13 billion light-years away, has managed to cross the edge of the heliosphere. The edge, not the interstellar medium. The boundary where the Sun's direct influence ends, not the stars. This is the scale of the problem, not the physics, not the engineering in principle. the actual current state. We have gotten one probe to the edge of the Sun's neighbourhood, and it took 35 years, and it is now about 23 billion kilometres away, and the nearest star is 40 trillion kilometres away. The gap between where we are and where we need to be to reach the nearest star in a human lifetime is not a gap of a factor of 2 or 10 or 100. It is a factor of millions. Millions of times faster, or millions of times more patient, or some combination of speed and patience that we have not yet found the right shape for. Knowing where you are is the first step toward knowing how far you have to go. This is where we are. The heliopause milestone matters because it is a real boundary with measurable properties, not an astronomical abstraction. The plasma environment changes at the heliopause. The density of galactic cosmic rays increases. The magnetic field configuration changes from solar to interstellar. Crossing the heliopause means entering a genuinely different physical environment. For any interstellar mission, the heliopause is the first real test of a spacecraft's ability to survive the interstellar medium, the first environment that cannot be fully replicated in any test facility on Earth or in Earth orbit. The voyage from Earth to the heliopause is, in a very real sense, the shakedown cruise for any interstellar mission. We have done it once, with Voyager 1, in 35 years, at speeds that are not remotely adequate for human interstellar travel in a lifetime. The Drake equation was written on a blackboard at the Green Bank Observatory in West Virginia in 1961. Frank Drake, the astronomer who wrote it, was trying to estimate the number of civilizations in the Milky Way that might be capable of interstellar communication. The equation multiplies together a series of factors: the rate of star formation, the fraction of stars with planets, the fraction of planets that develop life, the fraction of those that develop intelligent life, the fraction that develop radio technology, and the average lifetime of such civilizations. Drake's original estimate was in the range of 10 to 10,000 active civilizations in the galaxy at any given time. More pessimistic estimates, using lower values for the biological and cultural factors, give results less than 1, meaning we might be alone. More optimistic estimates give millions. The Drake equation is not a prediction. It is a framework for thinking about what we do not know. The factors that involve physics and astronomy, the rate of star formation, the fraction of stars with planets, are now known reasonably well from decades of telescope observations. The Kepler and TESS missions have given us robust statistics on planet occurrence rates around Sun-like stars. The factors that involve biology, chemistry, and culture are almost entirely unknown, but the Drake equation has a connection to tonight's question that is often overlooked. Even if intelligent civilizations are relatively common, interstellar travel faces the same physical constraints for any civilization anywhere in the galaxy. The energy requirements are the same. The relativistic time dilation is the same. The social and psychological challenges of generation ships or near light speed travel are likely to be similar. If interstellar travel is genuinely hard enough that no civilization survives long enough to achieve it, that would be one answer to the Fermi paradox. If it is achievable, but civilizations choose not to attempt it, that would be another. The answer to how far humans can travel in a lifetime is the same answer, in physical terms, as how far any civilization in the galaxy can travel in a lifetime. We're not uniquely disadvantaged by our biology or our history. We face the same constraints that any species with the same kind of chemistry would face. The physics does not play favourites. Whether we are alone in facing these constraints, or whether 1,000 other civilizations are wrestling with the same equations, is not known. The Drake equation's uncertainty is not a flaw in the equation. It is an honest reflection of how little we know about the prevalence of life and intelligence in the universe. The equation is useful precisely because it organizes the ignorance. It tells you which factors are known, which are constrained, and which are almost entirely unconstrained. The factor that current research is most actively working to constrain is the fraction of planets that develop life. The James Webb Space Telescope is beginning to provide atmospheric spectra of nearby exoplanets. Within the next decade or two, we may have the first empirical data points on whether life indicating atmospheric chemistry is common or rare. That data will narrow the uncertainty in the Drake equation in ways that might tell us whether we are likely to be alone in attempting interstellar travel, or likely to be one of many civilizations that have already done so. The concept of a one-way mission needs to be examined honestly, because it changes the answer to tonight's question in a fundamental way. Most of the energy cost of an interstellar mission is deceleration. To arrive at a destination rather than fly through it, you have to shed all the velocity you built up during the journey. If you accelerate to 20% of light speed, you need to spend the same energy decelerating back to rest that you spent accelerating. The round-trip cost is even larger, because you need to accelerate and decelerate twice. The propellant mass for a round trip at high velocity can be dozens or hundreds of times larger than for a one-way mission. If you accept one-way travel, the engineering becomes significantly more tractable. You only need to accelerate. You arrive at the destination still moving at cruise velocity, and your arrival is your death, or your flyby, or your atmospheric entry, or whatever your mission plan requires for a spacecraft that will never need to return. For crewed missions, one-way is psychologically distinct from suicide, though the distinction requires careful thought. One-way settlers are not dying. They are relocating permanently. The analogy is to every human migration in history that was effectively irreversible. The first humans to cross the Bering Land Bridge, the Polynesian settlers of remote Pacific islands, the colonists who sailed to continents they would never leave. One way does not mean no future. It means no return. The first crewed interstellar mission will almost certainly be one way. The energy requirements for deceleration at the destination, if the destination is even marginally survivable, make a return mission enormously more expensive. The cargo manifest for a one-way mission can include everything needed to establish a permanent presence rather than the equipment needed for a round trip. The crew can be selected specifically for permanent relocation rather than exploration and return. This reframes the question of the mission's purpose. A return mission is an expedition. A one-way mission is a founding. The people who go are not travelers who will bring back stories. They are the beginning of something that might persist, if the destination supports it, for as long as the civilization that launched them. That is a different kind of journey, a different kind of courage, a different answer to the question of how far a human can travel in a lifetime. All the way. You can go all the way. You just cannot come back. The one-way nature of the first interstellar missions will shape their design in ways that cascade through every other decision. Crew selection criteria change. The mission does not need people who can successfully return. It needs people who can successfully establish. The cargo manifest changes. Not equipment for exploration and return, but equipment for permanence. The psychological support systems change. The mission does not need to maintain the crew's connection to Earth for the duration of a round trip. It needs to help the crew transition to a new world as their only world. The training changes. Not training for a mission, but training for a life. The first interstellar mission, if it is crewed, will be designed around a destination, not a round trip. The settlers will be the mission. The question of what kind of civilization could actually build an interstellar spacecraft in a human time frame is connected to a framework proposed by Soviet astronomer Nikolai Kardashev in 1964. The Kardashev scale classifies civilizations by their energy use. A Type 1 civilization harnesses the energy available on its home planet, roughly 10 to the power of 16 watts. Humanity is currently at about 0.73 on this scale, approaching Type 1 but not there yet. A Type 2 civilization harnesses the energy of its entire star, roughly 10 to the power of 26 watts. A Type 3 harnesses the energy of its entire galaxy. The energy required for an interstellar mission at a meaningful fraction of the speed of a light, as we calculated, is roughly 10 to the power of 22 joules for a 100,000-ton spacecraft moving at 10% of light speed. This is a few times the annual energy budget of a Type 1 civilization. Achievable, in principle, by a civilization with our level of energy production if it devoted its entire energy output to a single mission for a year or more. Not the realistic budget of any civilization with other demands on its energy, but at least in the right order of magnitude. For faster speeds, the energy requirements rise dramatically. A 50% of light speed mission for a 100,000-ton spacecraft requires roughly 10 to the power of 23 to 10 to the power of 24 joules. At current human energy production rates, that is thousands to tens of thousands of years of total output. A Type 1 civilization in a year. A Type 2 civilization in a fraction of a second. This tells you something important. Interstellar travel at relativistic speeds is not a task for a civilization at our current developmental level. It is a task for a civilization that has grown its energy production by several orders of magnitude. Whether that growth is possible without destroying the civilization in the process is not obvious. Whether it takes centuries or millennia depends on choices that have not yet been made. But the goalposts are visible. We are not guessing at what kind of civilization could build an interstellar mission. We can calculate it. Type 1 plus a factor of a few. That is the threshold. We are at 0.73 on the way to 1.0. The distance to the threshold is measurable if the direction is correct. The universe is 13.8 billion years old. A civilization that crossed the Type 1 threshold even 1 million years ago would have had time to reach the stars and come back many times over. If we're alone, we have the chance to be the first. If we're not alone, the threshold is apparently one that other civilizations have crossed, and what they have done on the other side of it is the silence in the night sky. The Kardashev scale has been criticized as too simple, because it measures only energy use and does not capture the sophistication or the values of a civilization. A civilization that generates enormous amounts of energy for destructive purposes is not more advanced in any meaningful sense than one that uses less energy more wisely. But as a measure of what is physically possible for a civilization, energy availability is the right metric. You cannot build things that require more energy than you can generate. The stars are behind an energy wall. The height of that wall is determined by physics. The height of the wall we are currently at is determined by our current energy production. The gap between the two is real and measurable and has been declining, in relative terms, throughout human history. Whether it will keep declining fast enough for interstellar travel to be achievable within any particular time frame is not guaranteed, but the trend has been in the right direction for the entire history of civilization. Here is the honest summary of where the science actually stands, stripped of the optimism that tends to creep into these conversations, and also stripped of the pessimism that sometimes replaces it. The nearest star is 4.24 light-years away. At the current human speed record, reaching it takes 114,000 years. There is no crewed spacecraft on any drawing board at any institution with any funding level that could reduce this to a human lifetime. There is no engine design that has been tested or is in development that could do so. The gap between current capability and the capability needed for interstellar travel in a lifetime is not a small gap. It is a civilizational gap. It requires either a completely different energy economy or a completely different approach to propulsion, or both. The physics does not forbid it. Special relativity allows it. The matter-antimatter photon drive, if it could be built, could in principle achieve 1g constant acceleration and cover cosmological distances in a single biological lifetime. The wormhole and the Alcubierre drive would be faster still if the exotic energy conditions they require can be met. None of these devices exists. None of them is in development. None of them has a credible timeline for development. What exists is Breakthrough Starshot, a program to send gram-scale probes to Alpha Centauri at 20% of light speed using laser sails. The engineering challenges are serious and none are solved, but they are defined challenges in understood physics. A demonstration mission might be possible within this century. A mission that reaches Alpha Centauri might follow in the next century. No crude version of this concept is on any timeline. What exists in the near term is continued development of nuclear and electric propulsion for missions within the solar system. What exists in the medium term is the possibility of robotic probes reaching the heliopause and the inner Oort cloud on decade timescales. What exists in the long term is the question of whether a civilization with our energy budget, if it survived and grew for centuries or millennia, could build the infrastructure for genuine interstellar travel. That is the honest picture, not hopeless, not imminent. A very long project still in the earlier stages, whose endpoints are visible in the physics even when the path from here to there is not. The honest summary has one more element that belongs in it. The people who work on interstellar propulsion are not naive. They know what the energy requirements are. They know what the current technology can do. They know the gap. They work on the problem anyway, not because they expect to build an interstellar mission in their careers, but because they believe that the incremental progress made in understanding the physics and identifying the engineering obstacles is the necessary precursor to eventual solutions. The scientist who works out the failure modes of the Bussard ramjet in 1970 is not building an interstellar ship. They are removing a dead end from the map. The engineer who identifies the minimum reflectivity requirement for a laser sail in 2020 is not building a laser sail. They are specifying the problem for the generation that will eventually solve it. This is how hard problems get solved. Not by single breakthroughs, but by the accumulation of specific, detailed, honest analyses of what each obstacle actually is. There is a thought experiment that clarifies what is actually at stake when we talk about interstellar travel in a human lifetime. Imagine two scenarios. In the first, humanity solves the propulsion problem in 200 years and begins sending crewed missions to nearby stars by 2224. By 2500, there are human settlements around 3 or 4 nearby stars. By 3000, the expansion has reached perhaps 50 star systems within 30 light-years of Earth. Each settlement evolves independently. Communication takes years each way. Cultures diverge. In 10,000 years, there are hundreds of settlements, most of them no longer culturally recognizable as descendants of 21st century Earth civilization, but all of them biologically human, each one a living answer to the question of whether humans can survive and adapt in radically different environments. In the second scenario, humanity never achieves interstellar travel. The Sun eventually exhausts its hydrogen fuel in about 5 billion years and expands into a red giant, making Earth uninhabitable, if humanity survives. That long without expanding to other star systems, it ends. One star, one planet, one species, final. These two scenarios represent the only two long-run outcomes that appear to be available. Either we develop the capability to reach other stars, or we are ultimately confined to a single stellar system with a finite lifetime. The timeline on which this question matters is not human. It is geological. But the technology that would make the difference begins with decisions made on human timescales. This is why the question of how far a human can travel in a lifetime is not just a physics puzzle or an engineering challenge. It is the question underneath the question, not can we do it, whether we will eventually have to. Whether the long-run fate of biology depends on finding an answer that current physics says is possible, but current technology cannot provide. The stars are not optional on the longest view. They are the only way out, not for anyone alive today, not for anyone's children or grandchildren or great-grandchildren, but for the civilization that comes after them, the one that inherits the physics and the engineering and the ambition of every generation that worked on the problem and did not solve it but moved the solution a little closer. The stars are the only available future, and the fuel for that future is the work done now, when the answer is not yet available, on a problem whose solution would take multiple civilizational lifetimes even after the first genuine breakthrough. The binary nature of the long-run outcome deserves more emphasis than it usually receives. There is no stable middle ground in which humanity remains on Earth indefinitely, without eventually being eliminated by the sun's eventual expansion. The timeline is long, 5 billion years, but the endpoint is not in question. The Earth will become uninhabitable. Whether humanity survives beyond that point depends entirely on whether interstellar capability has been developed and deployed in the intervening time. This is not a cause for panic. 5 billion years is an unimaginably long time. The development of interstellar technology does not need to happen tomorrow or next century, but it needs to happen eventually. And the work that makes it eventually possible begins at each moment in which the problem is seriously studied and the obstacles are honestly identified. Let the pace slow down here. The numbers have come fast tonight, from 39,897 kilometers per hour to 20% of light speed to 1g constant acceleration to the edge of the observable universe in 46 years of ship time. Let them settle. What does it mean, stripped of the technical vocabulary, that a human lifetime is not enough to reach the nearest star at the fastest speed any human has achieved, but is enough to reach the observable universe's edge at 1g constant acceleration? It means the question of how far a human can travel in a lifetime is not a question with a fixed answer. It is a question with an answer that depends entirely on the engine. The human body, the human lifespan, the human capacity to experience and endure a journey, these are not the limiting factors. They never have been. The limiting factor is always the energy, the speed, the technology. And the technology is not fixed. The Apollo 10 speed record was set in 1969 with chemical propulsion technology that had been developed for about 30 years. The physics of matter-antimatter annihilation was understood in 1932 when Carl Anderson discovered the positron. The gap between knowing the physics and having the engineering has always been large and has always eventually been closed by civilizations that had a reason to close it. The distance to Alpha Centauri is fixed. It is 4.24 light-years. It is not going to change. The time it takes to travel there is entirely a function of how fast you go. How fast you go is a function of the engine. The engine is a function of the physics and the engineering. The physics is known. The engineering is in progress, slowly, in the way that all genuinely hard engineering problems progress. The question is not whether the answer will change. It will. The human speed record was not always 39,897 kilometers per hour. 30,000 years ago, the fastest any human moved was perhaps 50 kilometers per hour, sprinting. The trajectory from 50 kilometers per hour to 39,897 kilometers per hour required 10,000 generations of cumulative development. The trajectory from 39,897 kilometers per hour to 20% of light speed requires something comparable, or a civilizational shortcut that we have not yet found. The shortcut is what people are looking for. The trajectory is the fallback. Either way, the direction is toward the stars. It always has been. The range between lower and upper bounds maps onto a range of civilizational development that has historical precedent in miniature. There was a time when the fastest human travel was a few kilometers per hour. The lower bound of distance in a lifetime was a few thousand kilometers. The upper bound, determined by what the physics of horse-drawn vehicles permitted under optimal conditions, was higher but not radically different. As technology developed, the lower bound moved toward the upper bound and then exceeded what the previous upper bound had been. The same process applies to interstellar travel. The current lower bound is the Oort cloud. The current upper bound is the observable universe under 1g constant acceleration. The lower bound will move. History says it always does. Go outside tonight if you can. Find a dark patch of sky. Give your eyes a few minutes to adjust. The closest star visible to the naked eye from the northern hemisphere, not counting the Sun, is Alpha Centauri, visible from latitudes south of roughly 29 degrees north. From the southern hemisphere it is easily visible, a bright star in the constellation Centaurus. It is 4.24 light-years away. The light entering your eye left that star 4.24 years ago. The star you're looking at was, when that light departed, in the same state it is in now, more or less. Red dwarfs change slowly. You're looking at the nearest star, the nearest neighbour, the first destination on any reasonable interstellar travel itinerary, and it is 40 trillion kilometres away. The Apollo 10 capsule, the fastest human vehicle ever built, would take 114,000 years to reach what you are looking at. A 1g constant acceleration antimatter drive, if such a thing could be built, would get a crew there in 3.6 years of ship time. The gap between those two numbers, between 114,000 years and 3.6 years, is the gap between where we are and where we need to be. The star you're looking at does not know you exist. It does not know the Apollo program happened. It does not know that some species on the third planet of a nearby yellow dwarf has been pointing instruments at it for a few hundred years and wondering what it would take to reach it. The star is simply there, fusing hydrogen in its core at a rate that will keep it burning for another 4 billion years, orbiting the galaxy on a trajectory that will carry it a few thousand light-years before humanity, if it survives and solves the propulsion problem, might ever reach it. The distance between you and that star is real. It is not a metaphor for difficulty or challenge or the limits of human ambition. It is 40 trillion kilometers of actual space, measurable in the parallax of the star's apparent position as the Earth moves around the Sun, and at the right speed, under the right physics, a human lifetime is sufficient to cross it. Not today. Not for any person alive today. But in the physics, the permission is there. The universe is not refusing. The universe has simply built a very large gap between the permission and the means. What you are looking at is the first step in a journey that is physically possible, and currently impossible, and historically inevitable, if history continues long enough. Go look at the star. It is 4.24 light-years away. Know what that means. Alpha Centauri is not just a star. It is a triple system. Alpha Centauri A and B are a binary pair of stars similar in size and temperature to the Sun, orbiting each other at a distance comparable to the distance between Saturn and the Sun, taking about 79 years for one complete mutual orbit. Proxima Centauri is a small red dwarf orbiting the binary pair at a distance of about 0.2 light-years, loosely bound, taking about 550,000 years for one orbit. Whether Proxima b, the exoplanet orbiting Proxima Centauri, is gravitationally stable over geological time, given the perturbations from the binary pair, is one of the questions currently being studied. Whether the system as a whole hosts other planets that have not yet been detected is not known. The triple system is the most complex interstellar environment that would be encountered in any near-term interstellar mission. Understanding its structure in detail is part of the scientific case for sending any probe there, crewed or not. There is a detail about the relativistic travel calculation that tends to get left out, and it is the detail that makes the calculation feel most human, most personal, most strange. If you left Earth at age 25 on a 1G constant acceleration spacecraft pointed toward the Andromeda Galaxy, and if the physics worked as described, you would arrive at Andromeda at age 54, 29 years of your life spent in a spacecraft, accelerating and decelerating, experiencing the same gravitational force as if you were standing on Earth. You would eat meals, you would sleep, you would talk to your crewmates, you would watch the universe outside shift and stretch as you approach the speed of light, the stars ahead blue shifting, the stars behind red shifting, the observable universe contracting in front of you and expanding behind, the cosmic microwave background warping into a ring around your direction of travel. During those 29 years outside your ship, 2.5 million years would pass. Every human being you knew on Earth would be dead, along with every human being who has ever lived, and every human being who will live in the next 2.5 million years. The civilization that launched you would be a memory, then a ruin, then a geological record, then nothing detectable by the beings, if any, who inhabit the Earth 2.5 million years from now. You arrive at Andromeda. You're 54 years old. You have 20 or 30 years left biologically, if nothing goes wrong. What do you do? This is not a physics question. It is the question that follows after the physics is answered, and it is the question that the physics cannot answer. The physics tells you that you can get there. It does not tell you what you find when you do, whether there are planets orbiting any of Andromeda's stars, whether any of them support life, whether any of the life you might find is intelligible to you or you to it. It does not tell you how to live the rest of your years in a galaxy where no one has ever heard of Earth. It does not tell you whether the journey was worth it. That is the question that only the person who makes the journey can answer from the far side of 2.5 million years and 2.5 million light years, alone in a way that no human being in the history of the species has ever been alone. The physics makes it possible. The rest of it you would have to work out as you went. The phenomenology of near light speed travel is worth dwelling on, because it is so far from any human experience that the words used to describe it barely capture it. At 99.99% of light speed, the stars ahead are blue shifted into the X-ray range. You cannot see them with visible light instruments. The stars behind are red shifted into radio waves. The cosmic microwave background, normally spread uniformly around the sky, concentrates into a bright ring at 90 degrees to your direction of travel. The universe is not simply compressed in front and stretched behind. It is geometrically distorted in ways that have no everyday analogue. The apparent size of the observable universe contracts ahead of you and expands behind. The photons of the background radiation arrive at your forward sensors with energies that would be lethal without shielding. The experience of near light speed travel, if any human ever achieves it, will require entirely new perceptual and conceptual frameworks to interpret. The history of distance is the history of technology. Every expansion in the range of human travel has been enabled by a new tool, a new engine, a new material, a new understanding of the physics involved. 30,000 years ago, the fastest overland travel was the speed of a running human. About 20 kilometers per hour over short distances, much less over long ones. The domestication of the horse roughly 6,000 years ago doubled or tripled this. The invention of sailing vessels capable of ocean crossing, roughly 3,000 years ago, opened the planet's oceans but reduced the speed advantage to the question of how fast a ship could be sailed. The steam engine, in the 19th century, doubled overland speeds again and made deep ocean crossings reliable regardless of wind. The internal combustion engine brought automobiles and airplanes. The jet engine brought transatlantic travel down to hours from weeks. The rocket engine brought Earth orbit into reach. Each transition required a fundamentally different energy source. The horse replaced the human metabolism. The steam engine replaced the horse with coal combustion. The internal combustion engine brought higher energy density fuels. The rocket brought chemical energy densities orders of magnitude higher than anything before it. Each transition also changed what destinations were accessible. A running human can reach anything within a day's travel. A horse can reach anything within weeks. A sailing ship can reach any point on Earth given enough time. A rocket can reach low Earth orbit and, with enough fuel, anywhere in the inner solar system. The interstellar transition requires another fundamental energy density leap. Chemical energy cannot do it. Nuclear fission can improve things marginally. Nuclear fusion can improve them significantly. Matter, antimatter annihilation, is the theoretical maximum available under known physics, and it is sufficient if it could be harnessed. The question of when this transition happens depends on the priority assigned to it by the civilizations with the resources to pursue it. Nuclear fusion has been the next step in energy for 70 years, and we are still a decade away. The reasons are partly technical and partly economic, and partly the absence of the urgency that sometimes accelerates technology development beyond its normal pace. The stars will not wait. The physics will not change. The question is whether the urgency arrives before the capability is needed, and after the capability is achievable. Historically, the urgency and the capability have tended to arrive together. Whether that holds for interstellar travel is the open question of the next few thousand years of human history. The parallel with the history of aviation is not perfect, but it is suggestive. In 1903, powered flight was demonstrated for 12 seconds. In 1927, Charles Lindbergh crossed the Atlantic solo in 33 hours. In 1969, humans reached the moon. In 2024, commercial aircraft carry 4 billion passengers per year. The progression from 12 seconds to 4 billion passengers per year took 121 years and required advances in aerodynamics, materials science, engine design, navigation, air traffic control, manufacturing and maintenance that no one in 1903 could have predicted in detail. Each advance opened new possibilities that enabled further advances. The interstellar case is harder than aviation. The energy gap is larger, the distance gap is larger. But the precedent for technologies that seem permanently out of reach being solved through sustained civilizational effort is real. You've been sitting with these numbers for a while now. The Apollo 10 speed record and what it buys in a lifetime. The relativistic equations and what they allow if you have the engine. The engineering challenges and what they demand. The distance to Alpha Centauri and what 4.24 light-years actually means. Let them settle. Not as a list of facts. As a single answer to the question the title asked. How far can a human actually travel through space in one lifetime? At the fastest speed any human has achieved, in the best spacecraft ever built by our civilization at its current level of development, the answer is not out of the solar system, not to interstellar space, not to the heliopause, roughly to the inner Oort cloud, the shell of icy bodies at the outermost gravitational boundary of the sun's influence, less than a quarter of the distance to the nearest star. At the theoretical maximum performance allowed by known physics, under 1g constant acceleration using a perfect matter-antimatter drive, the answer is the observable universe, the entire span of everything we can see in every direction, traversable in about 46 years of ship time. Between those two answers is the entire space of human technological development. Where on that spectrum we can actually operate at any given moment in human history is determined by the energy density of the propulsion we have mastered. We are closer to the lower bound than the upper, by a large margin. But the upper bound exists, and it is as wide as everything there is. There is something in that, something that is not quite hope, and not quite humility, but something between them. The physics is generous. The physics says that the lifetime of a human being, 80 years, is not an obstacle to interstellar travel. It is sufficient. It is more than sufficient. Under the right conditions, it is enough to cross everything. The obstacle is not the life. The obstacle is the engine, and the engine is a problem of engineering and energy and time, not a problem of physics. The physics gave us permission. The rest is on us. The stars are 4.24 light-years away and 114,000 years away simultaneously, depending on the engine. Tonight, they are 114,000 years away. How long that remains true is, in the longest possible view, up to the civilization that inherits the problem. The comparison between the two bounds is the heart of tonight's answer. Not the physics, not the engineering, not the sociology. The gap. The gap between 39,897 kilometers per hour and the matter-antimatter drive that would allow 1g constant acceleration to the edge of the observable universe. That gap is not a distance. It is a density of technological development still waiting to happen. The distance to Alpha Centauri is 40 trillion kilometers. The number of technological generations separating our current propulsion from the propulsion needed for interstellar travel in a lifetime is unknown, but it is large. How large depends on how hard the specific obstacles turn out to be when confronted with the full resources of a civilization that has decided to confront them. That decision has not yet been made. The question is when it will be. You made it to the end. Not everyone does. The Tsiolkovsky rocket equation, and the Lorentz factor, and the matter-antimatter annihilation, and the Alcubierre metric, and the Bussard ramjet, and the generation ship sociology, and the Kardashev scale, and the 46-year traverse of the observable universe at 1g constant acceleration. It is a long way from 39,897 kilometers per hour to the edge of everything. You followed it the whole way. If any of this landed tonight in the way I hoped it would, not as a list of concepts, but as a genuine reckoning with the distance between where we are and where the physics says we could go, then there is something I want from you before you close this. Leave a comment. Not long, just your city and the time. That is all. Because the question tonight was about distance and where humans are relative to the distances that matter, and you are somewhere specific right now, at a specific hour. And that specificity is part of the answer. The map of where people are when they sit with these numbers is itself a kind of data. City and hour. That is the comment I want. The like button and the subscribe button are there. They do one thing. They send this to the next person in the next city at the next hour, who is sitting under a sky full of stars that are 4.24 light-years away and 114,000 years away simultaneously, and needs to understand both of those numbers at once. That person is out there tonight. The buttons are how this finds them. The nearest star is 40 trillion kilometers away. A human lifetime under the right engine is sufficient to reach the edge of the observable universe. The gap between those two facts is the entire history of a civilization's technological development, from the first controlled fire to the first matter-antimatter reaction. If that reaction is ever controlled, we are somewhere in that history right now. Early, by the look of it. Earlier than it feels. The stars have been there for billions of years and will be there for billions more. The question is not whether we will get there. The question is when the engine is ready and whether we will still be here when it is. The answer to that second question depends on choices being made now in the only lifetime any of us has to make them, at whatever hour it is where you are. Good night. The stars are patient. They have been there for billions of years and will be there when any answer to the propulsion problem finally arrives. The question of how far humans can travel in a lifetime is not a question that will be answered in a single generation or a single century. It is a question being answered progressively, experiment by experiment, calculation by calculation, gram by gram of antimatter produced, photon by photon of laser light focused on a sail in a laboratory somewhere. The answer is moving. It is not where it was 50 years ago. It will not be where it is now in 50 more years. The direction of movement is toward the stars. The speed of movement is determined by choices being made now, in the only lifetime any of us has, about what is worth working on, and what is worth funding, and what kind of future is worth building toward. There is a version of the lifetime travel question that does not involve biological humans at all, and it may be the version that matters most for the long run. Artificial general intelligence, if achieved, would not be constrained by the biological limitations that make interstellar travel so challenging for humans. An AI system does not age. It does not require food, water, or oxygen. It does not experience psychological deterioration from isolation or confinement. It does not die of radiation damage in the same way biological tissue does, though its electronic substrate has its own vulnerabilities. It does not need to arrive at a destination in order to reproduce. It can transmit copies of itself at the speed of light. An AI designed for interstellar exploration could be launched on a small, lightweight probe at a high fraction of the speed of light. It could spend decades of ship time in a low-power hibernation mode during the cruise phase. It could wake on arrival, survey the destination system, build infrastructure from local materials using von Neumann self-replication, establish a presence, and eventually create an environment capable of hosting biological life, at which point human colonists, either biological or reconstructed from transmitted genetic information, could follow. This is not a plan. It is a direction of thinking that a number of serious people in both the space science and AI communities have been exploring. The components are speculative but not physically impossible. The timeline would be long by human standards, but short by the standards of the galaxy. The question of whether an AI carrying human values, human knowledge, and human aesthetic sensibility as a human explorer in any meaningful sense is philosophical rather than physical. If the goal is to extend what humans are and what humans have built into the galaxy, an AI proxy may be the most practical vehicle. If the goal is to have biological humans experience other stars, the physics remains as demanding as we have described. For tonight's question, the AI direction suggests that the answer to how far humans can travel in a lifetime may eventually have a third form, beyond biological travel and mind uploading. Not how far a human body can travel, not how far a copied human mind can travel. How far a human civilization can project its presence in a form that preserves what matters most about that civilization. What matters most is the part we've not agreed on. The artificial general intelligence path to interstellar travel is controversial, not because the physics is uncertain, but because the values question is unresolved. An AI that carries human knowledge and human aesthetic sensibility and human cultural heritage to another star system has preserved something of what humanity is. But which something? An AI is not a person. It does not have the lived experience of a biological human being. It does not age. It does not fear. It does not love in the way that humans love. It might represent what humans have built and thought and created, but not what humans have been. Whether that is sufficient preservation of human identity for the mission to count as human exploration depends entirely on what you think human identity consists of. The physics says an AI can go to the stars. The philosophy has not decided whether that counts. The solar sail is a real technology. It is not theoretical, not in development, not waiting for breakthrough materials. Solar sails have flown in space. They work. Icaros, a Japanese spacecraft launched in 2010, used a 20-meter square sail of polyamide film to generate thrust from solar radiation pressure and to produce electricity from embedded thin-film solar cells. It was the first spacecraft to successfully demonstrate solar sail propulsion in interplanetary space, travelling from Earth toward Venus on a hybrid solar/sail trajectory. The physics was validated. The engineering worked. LightSail 2, launched by the Planetary Society in 2019, deployed a 32-square-meter solar sail in low Earth orbit and demonstrated sustained orbital acceleration using only solar pressure. It raised its orbit over several weeks using nothing but sunlight pushing on the sail. These are small-scale demonstrations. The force generated by solar pressure is tiny, about 9 micronewtons per square meter at Earth's distance from the Sun. For a large sail and a lightweight spacecraft, the acceleration adds up over time, but it is not the fast path to the stars. At Earth's distance from the Sun, a solar sail spacecraft could reach speeds of perhaps a few hundred kilometers per second over years of acceleration. That is about 0.1% of the speed of light. The journey to Alpha Centauri would still take thousands of years, but solar sails become more interesting when combined with a laser. Laser sails, the starshot concept, replace the diffuse pressure of sunlight with the concentrated intensity of a directed beam. A laser powerful enough to push a gram-scale sail to 20% of light speed would deliver, briefly, an enormous energy flux to the sail surface. The physics works. The laser is the technical challenge. For larger payloads, the laser power required scales dramatically. A 1 kilogram payload to 20% of light speed requires a laser roughly 1,000 times more powerful than one needed for a 1 gram payload. A 1 metric ton crewed capsule, assuming for the moment it could survive the acceleration, would require a laser 10 to the power of 9 times more powerful. That is 1 billion times more powerful than the proposed Starshot laser. The laser sail path to human interstellar travel requires solving the power generation problem on a scale that is, at this point, several generations of technology away. But the physics is not the obstacle. The physics is solved. The engineering is the obstacle, and engineering obstacles have a historical record of being solved by civilizations that have decided to solve them. The solar sail history extends beyond the demonstrations mentioned. The concept was proposed by Johannes Kepler in 1610, when he observed that comet tails always point away from the Sun, and speculated that some form of solar radiation might be responsible. He was correct. The force is real. Spacecraft have now demonstrated it in practice. The reason solar sails are not already the primary method of interplanetary propulsion is that the force per unit area is very small at Earth's distance from the Sun, and practical sails need to be large. For missions requiring high acceleration or short transit times within the solar system, solar sails are not competitive with chemical or ion propulsion. For long duration, low acceleration missions to the outer solar system, they are potentially the most propellant-efficient option available. The Starshot laser sail is a qualitative extension of the same physics, replacing the diffuse pressure of sunlight with the concentrated intensity of a directed beam, and making the acceleration arbitrarily large for small payloads.